Now we will continue with presenting the results in short pitches. So I want to remind the speakers again that we would really want you to stay to 8 minutes. And actually maybe following on the DG Agri story that was just said, it's maybe the perfect moment for Emma to explain the results from Boerenbond. So Boerenbond is a Flemish farmers cooperative. She will explain.
Hello, everyone. My name is Emma van Steenwegen. I work for Boerenbond, and I will tell you something about the insights that we discovered thanks to the Waste2Func project regarding the valorization of residuals from the primary sector. So for those who do not know, Boerenbond is the main Flemish agricultural farmer organization. We have a membership of around 14,000 farmers and also contact with 70,000 rural families. And our main goal is to advocate both for the interests for small farms and for big farms. Our objective in the Waste2Func project was to get an answer to what do farmers think about these kind of new business models regarding the transition towards the bio-based economy. And in the beginning of the project, we talked to many of our members and also non-members. And at that moment, it seemed that there were limited opportunities for small farmers, for small local family-owned businesses to valorize residuals. Because as you can see, many farmers responded negatively to the question whether they would be interested in valorizing their residuals. We have many known reasons for this as well, of course. So the well-known aspect of small, uncertain volumes that occur on the farm of these residuals make it quite difficult to establish a suitable and sustainable business model. Also, you can't forget that farmers often have simple, low-cost ways of valorizing residuals. It can be a collaboration with a neighbor farm or really a local way of closing loops. So there's this traditional way of thinking of what is the easiest way to, first minimize waste, but also try to optimize these residuals to optimize costs. And then one very important reason I think for these limited opportunities is also that the residuals are not valued high enough by all chain actors. Of course, the value of your residual depends on the crop type, depends on the composition. If there are a lot of carbohydrates in it, it's more interesting. But you always should take into account that in many cases, these residuals are not available to just enter the market. It can be that these residuals still reside on the field, and then the farmer has to put in time, labor, resources to collect this residual stream, potential packing costs or potential storage costs, and transport costs also need to be taken into account. So the benefit of this residual valorization pathway should compensate all these costs. But that's regarding the small local farms. Then we also tried looking at what other players would be would have interesting residuals. And then we looked at the processing farms. So farms who have themselves some processing installations, but also industrial processes. And these are some examples. In some of our workshops, we also discussed about auctions. So we interviewed auctions to see how they use their residuals, but we also talked to local policymakers to try to understand what could be the role of the farmer in this quest or this change towards bio-based economy. And then, we focused on main processors of potato, of sugar beet, and of fruits and vegetables, because these are the largest amounts of waste streams here in Belgium. Regarding sugar beets, there were in 2024, there were about 56,000 of hectares planted, also for potatoes, around 50,000 hectares. So in the Flemish part then of Belgium, so these are very large parties. We also talked to other agricultural organizations because we wanted to get an answer to or to get insight into how do other countries face this problem of residuals that occur on farms and that need to be optimally valorized. We had a lot of varying answers. It, of course, depends on the regional priorities. For example, for the Wallonie part of Belgium, they also said that the small scale of some farms limits potential investments or investments in technologies or investments in new valorization pathways. For example, Agrinos in Greece also said that large cooperatives can help farmers to access new valorization pathways. Large cooperatives also can assist farmers in working together with industrial parties, like in a Waste2Func project, because it's often a big gap, and you better your negotiation potential and pricing discussions by grouping farmers together, of course. So yeah, what was a conclusion based on all these interviews we conducted, all this information we gathered? It was actually an answer that we searched for the question, what do we see as the optimal collaboration with the farmers? And I tried to summarize our conclusions in a few points. So first of all, we think that there's a lot of opportunity in times of uncertainty. So especially last year during the autumn of 2023, it was a really wet year. A lot of harvests had problems with root rot in both potato rot, but also sugar beet rot and carrot rot, for example. These are all biomass residuals that occur due to climate change, and the farmers need to find additional pathways to try to save their harvest, you could say. Other examples or another conclusion was that these cooperative structures can unite farmers and can really strengthen their position in the first chain of this new value chain. Then, of course, processing farms do have larger volumes compared to small farms, so it could always be a little easier to access those residuals. And then finally, but really one of the most important things is this transparency and this trust and also flexibility between all the actors, especially in the beginning of this change. So between, the farmers and the waste collectors and waste processors. So, but I want to shortly touch upon again on this smaller farm. So how could we solve this problem? How could we potentially valorize these little volumes of residuals on these local small farms? And we try to look at, for example, the animal-based byproducts here in Belgium. These carcasses and all these animal remains are collected on farm by Rendak. It's a company who processes and destroys these products on behalf of the government due to thanks to public health reasons, of course. So we try to see, okay, what these kind of trucks go to the farms and they really collect small batches of biomass. So how could we try to elaborate this and extrapolate towards plant-based byproducts? In this case of Rendak, who pays for this kind of collection, it's of course the farmer through a kind of subscription to Rendak, but it's also the government because of these public health reasons. And then it's also, of course, Darling Ingredients, the holding beyond Rendak, because they benefit from developing new interesting end products from this biomass. So it's a question that that future projects or future priorities could focus on. Is this also possible, this small scale collection for plant-based byproducts? Because this is the only way that we could involve the whole of the primary sector. So that's actually the future perspectives that we wanted to focus on. So nowadays, the situation is that farmers with their biomass often drive to biogas producers. They need to pay for it, or they don't have to pay for it and it's break even, or they even receive a compensation. It all depends on the side stream composition. But also in the story of Waste2Func, for a collection of biomass for upgrading into lactic acid and biosurfactants, one should look into who should pay for these kinds of collection. Is it the farmer only, or is it also some kind of government body or waste processor? Because if we are about to benefit from all these high value products and it's based on low cost waste, then we think that the cost should be distributed equally among the chain. So, thank you for your attention.
Thank you, Emma. I think this was very interesting conclusions to think about. So now maybe the perspective from a large waste collecting company. So I'd like to invite Thomas Anne from Darling Ingredients. So is yours.
Hi, my name is Thomas, like Sophie said, Thomas Anne. I'm working for Darling Ingredients, Ecoson, the former group Op de Beek. So the last 4 years, different company names were used because we were acquired. And I'm quickly going to introduce the company names so everybody can follow. So, first of all, Darling Ingredients. 2 years ago, Group Op de Beek was acquired, or a part was acquired by Darling Ingredients International. It's international, so they have a headquarters in Irving, Texas, and for Europe they have headquarters in Son in the Netherlands. It doesn't really matter, but they have 200 locations worldwide, and they normally work around animal byproducts. And with the acquisitions like Group Op de Beek, they are introducing themselves in the market of organic waste in general. I don't have the time to. Sorry. I thought the room was small enough. And normally I'm too loud. So just quickly, Group Op de Beek Materials and Treatment was the first name introduced in the project, I think, and then Biogas Solutions as the waste collecting company. We are a waste collector and a waste processing company. So in the project, we were collecting the waste. We developed an application in the project to facilitate this collection. We are a waste processing company, so we also hosted the pilot of the lactic acid production. And we, of course, have information from the field to be shared with all stakeholders and partners. We were acquired, so first of all that, and then the names changed. So in group Darling Ingredients, I'm sorry, in Belgium you have Rendac, like Emma already said, Sonac and Ecoson. Rendac are dead animals, the processing of dead animals. Sonac a bit of the same, and Ecoson is the collection of organic waste in general. It's in the Ecoson branch that the group Op de Beek companies were acquired. And now you can see Op de Beek is becoming Ecoson Energy, Biogas Solutions is becoming Ecoson Materials, and Compovert is becoming Ecoson Nutrients. So all these names are possible that you can find them in the text of the project. It's all the same. We're still the same company, the same processes. This is our process. I don't have the time to explain it all, but the main line is that we collect organic waste. This can be in bulk, just potato starch from a potato processing company or sludges from a organic wastewater treatment facility. Or this can be packed waste coming from supermarkets, coming from restaurants. If you don't eat your plate at the lunch, then it's possible that it comes into our process at the end of the week. So we're going to treat, if necessary, on site. This means normally unpacking. We're going to separate organic matter from packaging material, mostly plastics, sometimes glass, metal, whatever. We do it manually or mechanically. And the goal is to make a kind of mix, energy mix, a soup that we can feed to the anaerobic digesters. So that's a natural process. It's a fermentation in a controlled environment. And the goal is for us to produce biogas, because the methane that we produce can be energetically valorized in a CHP, combined heat and power. So they will produce electricity, sustainable green electricity and heat. Electricity is used or sold to the electricity grid, and the heat is used in the post-treatment of the digestate coming from the digestion. I don't have the time to explain all the next steps for the digestate, but what we try to do is to take out the water and purify it and just discard it to the environment, and to concentrate organic matter and nutrients, and finally produce products that can be used as organic fertilizers. So all incoming material is leaving our site as a biochemical, an organic fertilizer, or clean water. Next is a very bad print screen of the scheme before. So as a group Op de Beek, just to explain that in this case it was the pilot of W for the lactic acid production, but also for Amphystar could be the same. In our process, we're aiming to convert organic matter, so lipids, carbohydrates, and proteins into biogas. But of course, there are other fermentation pathways like lactic acid. So the pilot is an interesting or a potential interesting step in our process where we can first of all produce lactic acid if it has a higher value, and then the remains, the digestate coming from this fermentation, can still be used for anaerobic digestion into biogas. And then you have all synergies that can be made. You can use the heat from the installation, the electricity from the installation. We produce ammonia water that can be used as a nitrogen source in the process. We have water, so demineralized water if needed. We have processed water on site. So there are a lot of connections to be made. So that was for us the idea to join the project. Of course, it's an alternative valorization route as we have today and as most of the anaerobic digesters have. So this brings the first question for a commercial company. Is it techno and economically feasible? What about regulation? Because we're using a waste, but we want to make a product. In Flanders, it's quite well managed, but if you cross the border, then the legislation is different. What's the market readiness? Is there interest? Is it going to cost more because it's a bio or a green or a sustainable product? And then the variety, because this is one possibility, Amphistar and Triple W, two possible pathways, but you also have insect insect farms. You have other fermentation pathways, you have biochemical conversion to produce methanol, ethanol, and all this kind. So as a commercial company, there are a lot of projects coming, and you have to select what we think is the best. So for this project, we were in the work package of the mapping and the optimizing of the feedstock, of course, and the supply chain, and then the demonstration of the biosurfactant and the lactic acid production on or off-site. A few pictures just to give you an idea of the type of waste we process. These are the easier ones. You see fruit and vegetables, you see donuts. There's probably a reason we can't eat them anymore, a microbial reason, or because they are frozen, not hard enough, or whatever. And then like pastry waste, above you have probably bananas from the other side of the world coming to our site. But we also have this type of waste coming from supermarkets, bananas that are already rotten, bananas that are very rotten and already become a milkshake in the trailer. So this is less easy, and this has a lot of handling to separate the organics from the plastics and the packaging. Some bottlenecks that we've seen in the project. So you have the former food waste, there's the packed waste, and you have the bulk waste mix. That's everything that has not much handling. For me, I always say aim to the difficult waste, because difficult means not everybody can do it, and it has a better cost. So there's a higher carbohydrate or lipid content to the costs. There is a lot of waste available. Legislation is becoming also more strict. From this year, all companies have to collect organic waste separately. So they are obliged to do it. It's a bit of a niche market because not everyone can unpack and can manage this type of waste. But of course, you have impurities, can be inorganic or organic. Inorganic means pieces of plastic, pieces of glass, metal that are still in the product. We have technologies to take it out. In this picture, you can see if you don't take it out, it will be in the fermenter. Okay. I will be a bit faster. Other drawback is the organic variety. You can see carbohydrate content is already varying, and then because of the freshness of the waste, you already have a fermentation on site. If it's already fermented, you cannot control it anymore. So this is one of the problems. Other bottleneck, pricing and sourcing. You can aim for a Cargill of Viterra companies with carbohydrate-rich or lipid-rich waste streams, easy to handle. But the question is this waste? And it's a competition, it's a market demand and supply, so you will pay more. And then bulk collection door to door, like Emma also explained. If you go to a farmer for a few kilograms or a few tons, this will cost a lot. It's complex and costly. And that's what we as Ecosol Recycling want to aim for. And in that context, we used the project also to develop an application. We did it as a web application and a mobile application. Of course, because for us it's beneficial as a company because we are paid to do this collection, but also because if we source this waste and we pre-treat it, we can use it in these new applications as in the project. So it's efficient, it facilitates, and it's a main platform for the information for the customers. I think it speaks for itself. It's a login and it's an overview. And that's a print screen from the mobile app. And 8 minutes are very short to explain everything. So thank you. I hope it's clear.
Okay, thanks a lot. And I think now it's me. So I just realized I think I forgot to present myself at the beginning. So I'm Sophie Lodens. I'm the coordinator of the project together with my colleague Estelle, who's in the back. And so we coordinate this project on behalf of BBI JU Pilot Plant. And I just want to explain in this short presentation who we are and what we did exactly in the project, because we did not only do the coordination, obviously. So this is a nice picture of our plant situated in Ghent, here in Belgium. So we were founded, so first of all, we are a multi-purpose pilot facility. We do process development, scale-up, and custom manufacturing of bio-based products and processes. I will come back to the details of that later. We were founded in 2008, operational since 2010, and basically we are open access, so anyone can come in and do process development or scale up with us. We are also fully independent, so we have no industrial shareholders. There are several investments being done by the EU, Flanders and the Netherlands for new equipment. Some of these are still ongoing. We have some quality labels, ISO 9001, and we can also produce food grade, as you can see. And these are approximately 178 employees. So we have grown steadily in the last years, actually. So this is then a figure of our plant. So we have several halls, and basically this shows what services we all offer. So we can do biomass pretreatment, biocatalysis, fermentation, green chemistry, and also very important downstream purification of compounds from one of these first four technologies. And that's often the most challenging step in the process. We obviously also have a lab, a technical department. We are a big plant, so we also need warehouse and logistics. And we recently also opened a new office and customer hub building. So it's quite big, worth a visit if you are ever in the surroundings. And maybe how to collaborate with us. We have a double business model, let's say, in a way. So we have, on the one hand, we do private projects. So that's bilateral for a customer. We can go from lab scale up to 75 cube scale in biomanufacturing. That's a fee for service model. It's always a confidential collaboration, obviously. So we will not communicate to anyone about the collaboration unless the client wants to have a testimonial about this. And also very important, all the IP remains as well with the customer. So 75 cube, this was the time in August when the 75 cube fermenter was placed in the building. So then the roof was still open, now it's closed, and actually now running its first process. On the other hand, we have public projects like Waste2Func. So like this one, we have many of them ongoing, mostly European in Horizon Europe, BBI JU, can also be Interreg or nationally funded projects. And actually, Waste2Func is a nice example of where these two intertwined a bit, actually, and nice things came out for public projects because of private collaborations and vice versa. And that brings me to what we've done actually in Waste2Func. So actually we started our private collaboration with WWW back in 2016 with a Super Bio voucher. I looked that up, I didn't know it myself, but so it was already a long time ago. And we also had the biosurfactant technology still combined at Ghent and BBI JU Pilot Plant, but Sophie will explain all about that back then. And we saw that that also worked on food waste. And then actually we decided, because there was this nice BBI JU call, that we could combine both technologies in the Waste2Func project, actually. And that also led in the project then to the founding of Amphistar, but I will let Sophie explain it after me. As Pilar also mentioned, we have two follow-up BBI JU projects that also came from this, and also a lot of bilateral work next to the project. So basically, it's a nice example of how this bilateral work and this public work nicely intertwines. And this is not the only example, actually, of how that nicely worked. So what we did then exactly in the project, so first of all, we established a demo hall. So we completely separated our gray hall basically from for waste valorization. So it was an existing hall that we separated from the rest of the plant. And there we have added a lot of refurbished and new technical grade equipment for the Waste2Func processes to handle the food waste basically. So there's a lot of potential as well with this equipment for future waste-based projects and processes. So now it's more tweaked and tuned to the Waste2Func process, but if we adjust parts a bit, we can also do other waste pretreatments with that equipment, so in other European projects. And that are already started up actually and ongoing. I mean, not the processes, but the projects kicked off as well. And in the project, we did a food waste pretreatment at 1 cubic meter scale. That was mainly for to have for Amphastar to have the feedstock for their fermentations. And this is actually an image of this gray hull with the gray floor. And this was actually the first food waste pretreatment while it was running a few years ago. And obviously, we also did quite some scale-up work for both WW and Amphastar because we are that's our business. That's what we do, the scale-up basically. So this was always in nice close collaboration with them. The processes were in that way also improved for both of them, and still was and still is a very nice and fruitful collaboration. And here you can nicely see the handover from the food waste to our process engineer, to Amphastar, to Ecover, in both cases. So this is in front of the fermenters that were used. So it's a nice example of a nice collaboration. And then maybe as a final thing, I just want to say, you've seen the video in the beginning. The video was also made by our communication team under the wings of our communication manager, Katrien, who's here on the top right of the picture. So she really put her heart and soul in this. And I also want to take this opportunity. Unfortunately, she's not here but I hope she's listening or will listen afterwards. But I really want to thank her for her enthusiasm. We had very crazy ideas. I think she really managed to make the crazy ideas in a wonderful video together with the video guys who did it. So these are some behind the scenes images, really nice. So that was everything we've done, and I think we can be very proud. Voilà. So this was me. And I will hand over the floor to Sophie Roelands. No, voilà.
Okay, thanks, Sophie. Oh yeah, stay here. Hi, everyone. So for me also a weird moment because Waste2Func was one of the last projects that we wrote it together when I was still working at BioBase. So yeah, it's a nice project coming to an end, and we made a lot of really nice things inside, and I will explain you a bit in the presentation. So at Amphastar, our main credo is making biosurfactants mainstream. And I hope you will agree after the presentation that's really what we're doing. As a company, we work on three main pillars, I would say. We have expertise in the pre-treatment of waste streams, because if you've looked well to the presentation of Thomas, you've seen that it's still quite murky stuff that you cannot just put into a fermentation vessel, which is quite expensive equipment. So you need to do quite a lot of pre-treatment. And the reason we started doing that is because we saw more than 8 years ago in another European funded project doing an LCA that, oh, surprise, using bio-based feedstocks for your fermentation and then comparing with fossil-based chemicals, we did not do so very well because the agricultural practices used to produce these feedstocks, the fertilizers, the water use, everything you really need to do to produce a feedstock has quite a big impact on the environment. So at that time, we started to think, maybe we should start looking at waste feedstocks. And eventually this project then came out. So that's also where we have a lot of expertise to start using waste as a valuable feedstock. Microbes, synthetic biology. So we are a spin-off from Ghent University and the BioBase Europe pilot plant. I started doing my PhD at Ghent University 2009, so it's already a long time ago. And our focus there was really to start developing new microbes that can convert whatever feedstock into valuable biochemicals, in our case, biosurfactants. So this is also something that really sets us apart, making new microbes, making designer molecules with them. And then production, as we are a spin-off from BioBase Europe pilot plant. All these technologies have also been developed and scaled up in the lab and then in the halls of BioBase throughout the years. So of course, there also we have, we're not just lab people. We know what works, what doesn't work, what are technologies that are available at scale. And so that's also something that is, of course, very valuable to bring new technologies to market. So then I come to surfactants, and I will give you a brief idea of this market and what we're trying to solve here as an issue. So still a lot of the products we use in our daily lives, our soaps, our shampoos, anything you use in your household or your bathroom still contains quite a lot of fossil feedstock or is produced from fossil feedstock. We all know that's not good. We should keep it in the floor, that fossil CO2 should not be released to the atmosphere. You have long supply chains to get the fossil feedstock to the production plant to convert that into the chemical that then goes into your shampoo. And the process to convert that fossil feedstock into those surfactants is quite harsh. So high temperatures, high pressures, toxic catalysts, and also toxic byproducts in the surfactants that are in your products in your households. So not so nice. Then, in the 70s, people started already to think, maybe we should start looking at bio-based feedstocks. And then the whole palm oil idea came up, which in essence is a good idea because palm is a really productive crop. But of course, if you want to start replacing all that oil-based chemistry with palm oil, then you need a lot of land. So deforestation comes up. And if we look now at the market, it's still quite small and it's a huge issue already. So I think you can also agree with me. It's not the solution for long-term future. Also here, the same processes are used to convert these feedstocks into the surfactants. And you have these long supply chains. Then maybe I will skip that one because I am afraid I will run out of time maybe. And then come to the Amphistar example. So you can in fermentation start using first generation feedstocks, sugar and oil. That was what I skipped in the previous slide. You use a biological production process. But then again, if you would then start producing that mass scale, you again end up in the same situation as the palm oil issue. You need land, you need a lot of energy, water to produce these feedstocks. So we decided, okay, we have to start looking at waste and side streams. It makes sense in an integrated biorefinery concept, circular bioeconomy. You can do local production, which has many advantages. You don't have any direct land use. We use mild biological production processes, so not high pressures, high temperature, toxic catalysts, or catalysts are microbes, so they're biologically and safe. And we can produce pure and biocompatible surfactant molecules with our technologies. And so in a whole, we're decreasing the environmental impact with these products. I already explained this. So surfactants are everywhere in our daily lives. So we can create a huge impact to start replacing those chemicals. We'll skip this one. And we see in the market that there's really a push now for all the reasons that I just mentioned, but also some new laws come up, for example, 1.4 dioxane, which is a toxic chemical in surfactants that are used in toothpaste, for example. So we see that the industry, governments, everyone is awake and wants, of course, sustainable and safe surfactants. So we set up the company 5 years ago, and now we grow to a team of 20 people. And then I will switch to the project because I'm running out of time already and it's not reacting anymore. Wait, now it's coming. So, the photo taken at Thomas's place where he works, quite a dirty feedstock. So this is the feedstock we wanted to start using and which we worked on in Waste2Func. It's really dirty. But when you start retreating it, you can get something like that, which we then scaled up at BioBase Europe pilot plant within Waste2Func. So as I mentioned, you cannot just put this in your fermentation. That will not work. We scaled the fermentation processes to convert these waste feedstocks. So we used 3 in Waste2Func into a final biosurfactant here as well. which you can have a look at. So it's fully waste-based. No first-generation feedstocks were used. And we made some nice promotion pictures here to see you can really make ingredients for personal care and home care ingredients with these waste streams. And that was all done within the Waste2Func project. So I think we can be really proud of that. We also did some performance evaluation, of course, because, okay, it's nice to make it, but it has to work. It works very well. And that also then urged Ecover, which was another partner in the project, to start using that ingredient in an ecological cleaning solution, which was brought to market last year, which we are very proud of. And also, again, Roel, props to you to making this happen, because it was not easy. And I think it's really brave for a brand to do this, because the dirty waste that you saw is really in there. Then maybe what's next? So we have already quite some check boxes. And of course, there are still some big plans ahead. We want to start building our own production plants, where also we hope that BBI JU will still support us, because I show here some projects that have led to the establishment of Amphistar, Carbosurf, Waste2Func, now Serves Up, all within this really nice program, where you have the drive from the industry to do something that really matters. So not just money to do crazy research, no crazy research that can be really translated in something that is real. And we saw, I mentioned a few people already, but there are many others in the project where we collaborated across the entire value chain. And that's also something big and BBI JU is pushing for, and which is critical. If we want to make bioeconomy work, it's critical. And then for the panel, still, of course, some food for thought. Regulatory and LCA are still big things that we need to solve to make this happen. And that's, some of the things we bumped into during the project, but that will come later in the panel, I think. And then a little bit over time, I'm sorry, but thank you for your attention. And
thank you, Sophie. And now Amir is joining online. So Amir, I think you can unmute your mic if you're still there.
Yep, I'm still there.
Okay, great. I will control your slides and you just tell me when I need to hit the next one.
All right, thank you. Nice to meet you all, everybody. Sorry that I couldn't join face to face. But I will present W and what we've done as part of the Waste2Func project. Next slide. So W developed a technology to convert food waste into lactic acid, which is a platform biochemical. But lactic acid can go to various types of applications, from food to cosmetics to cleaning, and also PLA bioplastics. So very diverse range of applications. Yeah, next slide. We solve two problems simultaneously. First, we maximize the value of food waste instead of being digested or incinerated or, God forbid, landfilled. But Thomas talked a lot about food waste, so I'll not waste my precious time on that. However, with respect to lactic acid, current lactic acid production is being performed from food crops, such as sugarcane and corn. What we want to do is to replace food crops feedstock with food waste. By doing that, we also eliminate the need to place production facilities in places where sugar is very cheap, like Thailand. So we also save the freighting. We can also build much smaller facilities compared to the benchmark industry, which will result in local production in the EU. And doing all of that, and also keep a very environmental process. So the process is carbon negative, has carbon negative footprint. Next. So this is the process in a nutshell. We take the food waste, we ferment it using our proprietary microorganism. after the fermentation process, we clean the fermentation using our proprietary downstream processing and purification technologies until we get to the pure, nice, clean, transparent lactic acid. The lactic acid can then go to be used as feedstock for the PLA production. We go back to the process in the PLA recycling, where we can bring the PLA back directly to the lactic acid production. Of course, it's more techno-economical because PLA is pure lactic acid. Yeah, next. So if we can show some short comparison between us and the legacy producers, with respect to carbon footprint, like I mentioned, we have a negative carbon footprint. We don't use any land because we don't need to grow crops. We just use the food waste coming from these crops. Traditional lactic acid producer have gypsum byproduct. We have none. We have only compost that can then be used in places such as Darling ingredients. From respect to lactic acid derivatives such as lactate salt, which is also another product coming out of the lactic acid. So legacy producers need to produce it in an additional step while it is built in our process to produce the lactic salt. And like I mentioned, we can have much smaller facilities, and we can produce wherever there's enough food waste, which is almost everywhere. Next. So this is how it looks like. We take this brown, messy, smelly food waste. We ferment it until we get to this brown soup. We clean the brown soup, make the pure lactic acid, which can then be used, for example, in Ecover product. And like Sophie mentioned, both of the Sophies mentioned, Ecover did an amazing job putting this type of products into the market. I really think it was a game changer for all the parties involved. Next. In the Waste2Func project, we wanted to scale up the process, optimize the process so we will have the best techno-economical performance, reach the same quality in every batch. So we can reach the quality, but also make it repeatable. Yeah. Next. So first thing first, during the project, we established the demo site at Darling ingredient site. Next. This is how it looked like before we started establishing it. We used the Darling site. We had like 100 square meter of land. Next. And we started building the fermenter. We built it, manufactured it in Israel, did all the design. Then we added some additional equipment in step 2 and 3 until we got to the complete demo site. Next. And this is how it looked like. The picture in the right is the first time that we pumped food waste from this real food waste treatment site with everything that it entails to our fermenter. Next. Like I mentioned, another work package was with respect to the lactic acid optimization. Yeah. Next. Where we were screened for many strains and microorganisms, and we worked very hard to decrease the process time and have the best process possible. So because always from day one, we had in mind to reach to the best techno-economical model. We also use different types of waste, like waste streams coming from the dairy industry. Next. As part of the optimization, we also performed downstream processing optimization, where we showed that how we can polish and clean the lactic acid to get the nice, transparent, pure lactic acid that is required for the end application and for the PLA production. Next. We used many types of food waste streams, such as bakery waste from Vandermutelen, corn waste from ADM. In the new project that we're doing, we will also use wood waste. We used brewery spent grain. There's a lot of it in in Belgium from all the beer companies. Okay, next. And then, like throughout my presentation, I mentioned that everything was in with respect to the TEM, and we shown in the demo site, in all the runs that we performed, that we were able to reach very nice yields as we foreseen in our TEM model. Next. Now, the most important thing, two additional projects. One circle project, a flagship project based on the Waste2Func. We were able to be given the opportunity to establish under the BBI JU, of course, flagship program, to establish our first of a kind facility in Orga World. It's a renewable company with amazing partners, Biobase, of course, but also LG Chem, which is one of the biggest chemicals companies in the world, Volkswagen Group, that will test the PLA that we'll produce from the lactic acid in this site in car parts. We have Ecover to produce additional products from our lactic acid. Venus, an Italian personal care company, to open a new route of product for W lactic acid. And this project was kicked off September, but it's very exciting, and we look forward to accomplish that. Next. Now, recently, it was already announced that we reached to the grant preparation for a future what we call future project. It's under the EU Innovation Fund. Not signed yet, but we were awarded with the opportunity to get to the grant agreement. This is an independent site. You're making it faster, Sophie.
Yes.
It's not fair. This will be an independent site which will use monostreams, and we already started building our demo 2.0 in the next gen district, where future will be located, co-located with next to our demo. Our team in Belgium is growing. Tal already moved there. I will move soon, and very exciting times for W. Poof.
Yeah. Hello. Done. Okay. Thanks, Amir.
Thank you.
Great. Okay. And then we continue to the end users. So first of all, I would like to give the word to Monique van Lochem from Ivanek. Voilà.
Thank you very much for inviting us to say how we how we like your products. Let's say that way. Okay. Go this way. So, feedstock transformation in the surfactant industry. I want to focus in this presentation a little bit on the surfactants, biosurfactants. As you all know, it's also said already before that the environmental concerns drive, let's say, us in more sustainable solutions. This is let's say, an ongoing process in the world, and it means that innovators have to work on new products to improve the emission, and also to contribute to a more and nicer ecosystem. And if you look at surfactants, for instance, and products in general, there are always two parts. You have the ingredients and you have the packaging. And today here we focus more on the ingredients. And there are a lot of topics nowadays which are important if you look on sustainable solutions. But for instance, biodegradability, tropical oil use, and let's say locally produced and concentrated products are one of those more highlights. So feedstocks today, as the products are now, they are not fulfilling these sustainable requirements at all. So for instance, if you look at a surfactant, basically a molecule which is a surfactant always has two parts, an hydrophilic and an hydrophobic part. And to make them, you need somehow hydrocarbons and let's say they are for most of the products coming from fossil raw materials or from oils, which is already mentioned earlier, and that in itself was a good idea to use palm oil. But to get this palm oil, that has a lot of, let's say, negative effects like deforestation, etc. So it's not the final solution. So we need really to rethink about our surfactants feedstock. So from hydrocarbons to carbohydrates and beyond, we have to change there something. And nowadays, if you're talking about sustainable raw materials, it's not enough anymore that you say it is green. It's nice if it's green, but that's not enough. It has to be, yeah, it need to have some additional values, and we are much more critical. So we are thinking about product safety, but also emission reduction, competition with food, but also recycling of waste. That's where the Waste2Func project, of course, is a very nice example of biodiversity. That are all, let's say, items which are more and more important nowadays. Biosurfactants, where are they used? This is just an overview. I will keep it short because I think it's in the meantime clear for you where biosurfactants can be used today. As Evonik, we focus a little bit more on the personal care and household cleaning. As end consumers, as you are sitting here, personal care, medical care, household cleaning are typical, let's say, areas where you use products which contain surfactants or biosurfactants. So we, as Evonik, we really want to go beyond what has been done so far with biosurfactants. And one of our products who goes in that direction is the ReoFerm product, sophorolipids. And that means that we want to be gentle for people, but also gentle for our planet. Gentle for planet, for instance, means that you produce something that when it comes finally in the environment, that it will not stay there forever, but that the biodegradability is very quick. So, for instance, that the aqua toxicity is very low. You can see here in this diagram a nice overview where we compare our ReoFerm products, and the ReoFerm SL1 is a sapphorolipid product with more conventional surfactants like APG and SLES. And the higher the bar, the lower the toxicity is, because that is, let's say, more the speed of degradation. So you can definitely see here that those biosurfactants are performing much better than the more conventional surfactants. Of course, it's nice if let's say the product is good for the environment, but in first place it should also be nice for your skin. For instance, if it is used in a cosmetic, you still want that it is also nice for your skin, and that is the really the nice thing, that the biosurfactants, and they are even much more mild, so gentle for your skin than normal surfactants, and that you can see here in this picture. I think this picture say a little bit more maybe than those graphs here, but this is an example of a conventional surfactant. So you can see this is a test where they put a patch on the skin for 24 hours and then take it off and then see what the effect is on the skin. Now here you can see that, let's say, with a conventional surfactant, it's really a red. This is another one which is a little bit better, but you can see here the ReoFerm SL1, so the sapphorolipid one, and the Randoris one. You don't see any difference with the control, and that's also what you see here. So this is one example of let's say benefit of a biosurfactant. Another example is, for instance, in household cleaning. So you all know the washers, and I think you also realize that if it's finished and you open, you don't want to wait forever until it is dry. You want that it is dry as soon as possible. And you can see here that using these products, that the drying is, let's say, improved much more than, let's say, with competitor normal surfactants. And that means that the performance is better and that you don't have to wait so long. Another example here is, this is a kind of test what we do. So you put a standardized dirt on the plate, and then there is a machine that's scraps, and then after in this case 35 scrapping circles, you see or you check how much of the dirt is gone when using different products. And here you can see in the first example that is only a rhamnolipid product containing. This is a product which is a mixture of sophorolipids and rhamnolipids, and this is a benchmark product, and this is another let's say more eco-friendly formulation. And here you can clearly see that especially the one with the sophorolipid outperforms the other ones. So if you compare all those results, then for us it is very clear that waste-based sophorolipids still give a very high performing and at the same time is very mild. So the Waste2Func project provides an excellent opportunity to develop the process and in let's say in a further direction from to use really waste. You have to realize that the proposals I show here, they are used with done with sophorolipids, and we see similar results when we use the sophorolipid produced from waste. So that is you don't see any negative effect. It's as good as other biosurfactants. And we think that this is yeah, really, let's say, a nice way of introducing and the right way forward. So for us, it's waste-based sophorolipids bring, let's say, really to a next step and next generation for material transformation. And yeah, closing the loop with waste-based sophorolipids, we think it's really nice. Thank you.
Okay, thanks a lot, Monique. We will conclude then with
Okay. I feel like I'm being sabotaged on time now. This doesn't count, huh? Are you okay or? Okay. So a great example and something that got us thinking, what else should we be doing? What else can we do? We were already in conversation with both, well, I'll say with Triple W, on the technology prior to the project. So it didn't take a lot of thinking to say yes when we were invited to join the Waste2Func consortium. I will be talking about what we've done in the project, but in reality, I want to focus on only one of the 3 bullets that I have on the screen here, conscious of time. So obviously, when Triple W and Amphastar started generating samples, it was our task then to see, okay, how can we really make this into products then? How does it compare to industry standards? What impurities are there? How can we solve the technical challenges? So that's bullet 1, technical validation of both materials. And secondly, and this is a very important point, how to work on the consumer validation of these technologies. Likely these ingredients, they will come with some kind of like a downside, right? So it can be price, or it can be slightly different effects. So we need to explain to the consumer why they are buying this product, why there might be a slight green premium. So how you position the story is super important to a consumer. I'll have some great slides on that. And then obviously, iteratively, we kept working on the business side of things as well. And we're still working on that, right? So if there's a green premium, what products, that's all right. What products do they fit in best? That can do with concentration. So I'll spare you the details, but the business case is really, really important for us as well. So some slides on technical validation, but really briefly. So we did a lot of testing of the ingredients, trying to understand what's the right quality of the ingredients we need, which impurities can we tolerate, which one can't we tolerate. We're looking at a different process, production process than how it's made standardly. So this was a very important task. This was a lot of work, but it was also a little bit boring, so I will spare you the details on this. Important to note is that from a performance point of view, there is no leeway here. This needs to be on par with what's currently in the market. So for lactic acid, it's a descaler mainly in the formulations. So we made sure, and that's what you see here on the right, that it was exactly the same as what's currently being used in the product. So, and that was very nice. That was very clear. That's what's happening. So that's good. We did the same for the lipids for the biosurfactants. Monique already did a lot of a better job than me, detail-wise, explaining you how this is the case and what type of testing we've done on this. But in short, we found that it was equally performing as the commercial ones. Great news again. Then we had 2 ingredients that we can start using into products, specific products, looking at the business side, what's the best fit here, how can we tune this into the best possible products, and that's when I skip to the consumer validation part. So initially, we had 3 different products. We had a toilet cleaner, we had a multi-surface spray, and we had a fabric softener as well. We put this in front of consumers to start learning, okay, how do we speak to the consumer about these complex technologies or the feedstocks? Most consumers don't really know that there's palm kernel oil derivatives in their products. So lovely story, Sophie, but for a consumer, it's basically worthless. So we need to start thinking about clever ways about how to bring this to the consumer, right? So we've done that. Again, you're not going to the details. The fabric softener fell off. Everything that contains waste-based products that's too close to the consumer, and then I'm thinking personal care or I'm thinking laundry products close to skin, that was a big no-no. So we took that learning and then we ended up with a lot of different other prototypes. So we've also tested the narrative then. So on the left, you see something close to what's ultimately made it to market. Waste focused. In the middle, it more spoke to the palm kernel oil, the story that Sophie brought in. And on the right, it had to talk with, it had to do with like circular ingredients. It was too close to packaging circularity, so that all fell off as well. So I will skip the insights. I think I had the most important ones just now. And so we ended up with then the prototypes that are now here. They were commercialized. They've already been on the screen. They are here. So it's a toilet cleaner on the left, 81% food waste, excluding the water. A multi-surface cleaner on the right, 97% food waste content, excluding the water. So amazingly high contents of food waste and in both products. And we've commercialized these. So We made 2,000 boxes of combination of the products that we sold D2C. And had great response on that. I have a lovely video. It's on the website. I suggest you look at it
Food
yourself
waste.
because I'm
From
out of time. No, yep, I'm out of time, please. Welcome. Great consumer response, sold out really quickly. A lot of online engagement from consumers on LinkedIn. We did some sharing with some stakeholders within the community as well. So it's very clear now to our suppliers what we want and what we're looking for. In short, a great success. This is one of the most successful projects I've ever been part of. So I'm really proud to be standing here and to have the products with me. I want to thank everyone else involved because this is very much a team effort. And the output shows for that. So very quickly, some remaining hurdles. And this is only, I'm echoing what everyone else will say, but clear LCA frameworks, very important to assess the sustainability profile. Same for anything that gets me labels on the bottles. Talking to the consumers is really difficult. I need a good label that does most of the work for me. Non-existent today. Business case stays really important, and then consumer understanding and perception, and that's a challenge for ourselves. How do we talk to consumers in a better way about these types of novel technologies? 2 follow-up projects, part of both, really proud again. Surf's Up, and it's not on screen, but it's on my screen. So Surf's Up is one, and then Circle is the other one. So we're part of both, emphasizing our continued interest in this topic. Slightly over time, but I did my best. Thank you.